So this is a worksheet that I've put together to kind of summarize what happens to a glucose molecule as it goes through glycolysis, pyruvate oxidation, and the citric acid cycle, and after which all of the substances that are coming out of this are generally like ATP, NAD, and FAD. They can move on then to the electron transport and chemiosmosis to go through ATP synthesis. So I've posted this as a PDF on Canvas within modules within chapter 9. And I just want to go over this slowly with you to cover what's going on with the glucose molecule. So we're going to start with glucose here at the top, okay? And remember that's C6H12O6, okay? I'm going to move this down here. Bear with me for a minute here. And what I want to do is focus on what's happening right here at the top, okay? What's happening here at the top is in the cytoplasm, okay? This is going to be glycolysis. Sometimes people like to refer to it as glycolysis because the term lysis means to split. And glyco refers to the glucose. So glycolysis as a process is when we take a glucose molecule and we break it in half. So if you think about that logically, each glucose is made of 6 carbons. If we're going to break the 6 carbons in half, we're going to get 3 and 3. All right, so this is a hydrolysis reaction. Water is used to do this, to break the covalent bonds. So I want to show my 6 carbons of the glucose as these circles here, okay? And we're going to watch how those circles move. So during glycolysis, which occurs in the cytoplasm of all cells, prokaryotes and eukaryotes can carry on glycolysis, the first thing that we need to do is we need to destabilize the bonds of the sugar so that they'll break. And we do that by putting in 2 ATP molecules. So by putting some energy in, we cause the electrons to destabilize, and that will cause the sugar to split in half. What's really cool about that is at the end of this process, we actually make 4 ATP. So now that's going to be a net of 2. Because remember, just like if you're playing with the lotto, right? You know, you pay $2 for a ticket. Ooh, you made $4. No, you didn't, because you paid 2 for the initial ticket, so you only made $2, but you still made 2. So that's the payoff here. So we call this the energy investment phase versus the energy payoff phase. Because the process of cellular respiration is not only to completely disassemble and break down a glucose molecule, but also to produce ATP. So if I'm going to break this in half, I'm going to put 3 carbons over here and 3 carbons over here. And these little 3 carbon compounds are called pyruvate. They're called pyruvate. And so glycolysis starts with 1 glucose molecule, but it ends up with 2 3 carbon compounds called pyruvate. Now, when you're breaking bonds, okay, the things that are moving around all the time are generally hydrogens, but also sometimes some oxygens, some phosphates and things like that. Because remember, this chemical reaction is occurring in the cytoplasm, and the cytoplasm is a chemical soup. And there's all kinds of elements and things floating around in there. So one of the things that's going to happen is 2 NADs are going to come in, and they're going to come out as 2 NADH. They're going to pick up hydrogens. And when they pick up those hydrogens, they're also picking up electrons, okay, high energy electrons. So we call the NAD a high energy and electron carrier. It's a carrier molecule. It is a nucleotide compound, but it's a carrier molecule, and it carries the hydrogens and the electrons to the electron transport chain where they can be converted into ATP energy. So in glycolysis, which happens in all cells, in the cytoplasm, we start with glucose, 6 carbons. We're going to use 2 ATP. We're going to have 2 NADs come in. We're going to end up with 4 ATP, a net gain of 2. 2 NADHs, that's a net gain of energy in the hydrogens with the electrons, and 2 pyruvates. Now, we want to completely disassemble the sugar. We want to produce 6 carbon dioxide gases, and right now we haven't produced any because all 6 carbons are still tied up into compounds that are carbohydrate type compounds, and now they're in the 2 pyruvates. So we're going to move on to the next step. Now, the next step is going to be called pyruvate oxidation. And pyruvate oxidation, or the oxidation of pyruvate, if you think about the term oxidation, okay, oxidation versus reduction, when things are oxidized, okay, they lose electrons. So we're going to start breaking bonds to release more electrons. Therefore, we're going to make more NADHs because we always have to have our carriers in there to pick up those electrons and with hydrogen ions and move them to their final place, which is going to be the production of ATP. So notice where this is occurring. This is going to occur in the mitochondria. It actually occurs right at the mitochondrial membrane. So basically these pyruvates, they have to cross into the mitochondrion, and when they do, boom, this reaction occurs right at the outer membrane and in between the outer membrane and the inner membrane of the mitochondrion. So the first thing that's going to happen as the pyruvate is crossing into the mitochondrion is a carbon dioxide is going to be released. Okay, and that's going to happen on both sides here because remember that we've got 2 pyruvates, and each one is going to go through pyruvate oxidation. Now, if I remove a carbon as gas here and I remove a carbon as gas here, we're going to end up with a 2-carbon compound down here, right? Because 3 minus 1 is 2. So we're going to have 2. Now we're down to 2 and 2. And the name of this is acetyl. And I'm leaving a blank here because we're going to add to the name. Acetyl or acetyl, okay? Now, when we break off that carbon in the form of CO2 gas, we're going to release hydrogen ions and electrons. So we're going to make NADH here, and we're going to make NADH here. Now, the key here, you see this arrow is coming in. Something's coming in. It's not coming out, it's going in. This is called coenzyme A. And we need 2 of them because the coenzyme A is another type of carrier molecule, and what it's going to do is it's going to attach itself to this little 2-carbon acetyl, which still has a lot of energy in it, and it's going to carry it into the citric acid cycle. So we call this acetyl-CoA because it's the 2-carbon acetyl attached to our little coenzyme A. And all of this occurs, the pyruvate oxidation, at the membrane as the pyruvate is entering the mitochondria. And of course, this is in eukaryotic cells. Now, on this diagram, I didn't have a whole lot of room to show all this. So let me kind of back that up a little bit. What I want you to be aware of is that we've got 2 acetyl-CoAs here. Each one of these has to enter a citric acid cycle. Now, what you just saw occurs at the membrane of the mitochondrion. The citric acid cycle is going to happen in the interior of the mitochondrion, okay, which is you have an outer and an inner membrane of your mitochondrion. The inner membrane is looped into cristae, and then the fluid in the center is called the matrix. So this occurs in the matrix of the mitochondrion. And so everything that's happening on this side here is going to happen on this side here. You're going to have another citric acid cycle here because each one of those acetyl-CoAs has to enter the citric acid cycle and be completely disassembled. So I like to think of these chemical cycles, and I picture in my head a merry-go-round, okay? And as kids, you jump onto the merry-go-round and you hold on to the horse, or you get on the horse and the horses stay. Like, people jump on and jump off, but the horses stay. And that's because in order to go around, you have to hold on to something. So in these chemical cycles, you have members of the cycle that are there all the time. And one of them is a 4-carbon compound. It's called oxyl acetate. You don't need to know that. But I'm going to draw 4 open circles because remember, our carbons up here are dark circles. And so what happens is this 4-carbon compound that's in the citric acid cycle is going to cruise up this way. It's going to meet with the acetyl group. It's going to form a 6-carbon, which is called citric acid. And that's going to be 1, 2, 3, 4, 5, 6. So it's the 4-carbon compound, the oxyl acetate, chemically bonded to the little 2-carbon from the acetyl-CoA. Now, the CoA, the coenzyme, is simply a carrier. It's like an Uber. And so it has to drop off its cargo. So this is going to drop off and go back up. So it can pick up another one. Same one over here. It's going to drop it off and go in. So the only thing that actually goes into the citric acid cycle are these 2 carbons, the acetyl. Okay? So the acetyl is going to bond with the oxyl acetate, and as it comes around here, it's going to form a 6-carbon compound. Now, one of the first things on this cycle that's going to occur is that a CO2 is going to come off. And when that CO2 breaks off, we're going to make NADH because we're going to release electrons and hydrogens. And that's going to give us a 5-carbon because if you have a 6-carbon and you minus 1, you get a 5-carbon. And that 5-carbon is 1, 2, 3, 4, and just one of those. Same thing happens on the next turn. We're going to make a CO2 gas, and then we're going to have NADH, and we're going to end up with a 4-carbon again. Okay, 1, 2, 3, 4. Now, in order for this compound to be able to keep going around and around, it has to go back into this formation, has to have the right structure in order to receive the acetyl. So there's some swapping around that goes here. We end up making an NADH here. We make an ATP directly. And then we make something called FADH2, which is very, very similar to NAD. It's just a carrier. It's a hydrogen and electron carrier, but it carries 2 hydrogens and 2 electrons, whereas NAD carries 2 electrons and 1 hydrogen. So on this side here, you're getting the same thing. You're going to get your CO2 over here. You're going to get a CO2 over here. You're going to get your NADH over here, your NADH over here, and then over here, your NADH, your ATP, and your FADH2. And those numbers are important because right now, you've made 1 ATP here. You made 1 ATP here. That's 2. You made 2 ATP up here. That's 4. We're supposed to make 30 to 38. Yeah, 30 to 38. We've only made 4. And that's because of what's down here at the bottom. NADH and FADH2 move to the electron transport chain for conversion into ATP. Okay? And so if we just kind of look at this all together, we have glycolysis, we have pyruvate oxidation, and we have citric acid cycle, right? Well, we made 2 ATP here, and we don't make any here, but we make 2 here, okay? But we did make NADHs, and we did make FADH2. So in glycolysis, we made 2 NADHs. If we go back up here, okay, 2 NADHs. What did we make in pyruvate oxidation? Oops, 1, 2. So we made 2 in pyruvate oxidation, okay. How many did we make in citric acid cycle? Oh, well, let's count them up. We make 1, 2, 3, 4, 5, 6. So we make 6, okay, 3 on each one. What about our FADH2s? We make 1 over here and 1 over here. So we make 2 here, we make 0 here, we make 0 here, okay? So grand total, when you look at the bottom here, grand total is 4 ATPs, 6, 7, 8, 9, 10 NADHs, and 2 FADH2s. So this is where all our energy is still locked up. It's in the, it's on, I should say, the energy carriers of the NAD and the FADH. And so they're carrying these high energy electrons and hydrogen ions that have to move to the inner membrane of the mitochondria. That's where the electron transport chain is. They, like Ubers, they're going to drop off their cargo. So the NADH drops off the hydrogen and the electrons, comes back off as NAD. Your FADH is going to drop off a hydrogen and 2 electrons. So it comes in as FADH2, comes out as FADH. And so these are the primary carriers of all the energy that was stuck in the bonds of that glucose. And think about this logically. If you look at our overall equation, okay, if I turn this over and just go to C6H12O6 plus 6O2, right? Those are our reactants. Our products are 6CO2 plus 6H2O. Okay, think about this in terms of calories. Carbon dioxide gas, oxygen gas, any calories in those? No. 0 calories, 0 calories. Water, any calories in water? No, 0 calories. Is there calories in sugar? You betcha. There is, yes. 4 kcal per gram. So, if you start with a reactant that has energy, measurable energy, and then you end up with products with 0 energy, that means that the energy came out. It came out. And where did it go? The energy was used to take ADP plus PI and produce ATP, a high energy molecule. So, watch some of the YouTube videos that I've posted. I've got 2 really good ones that are posted on how the electron transport chemiosmosis works. If you have any specific questions about this process, email me. The other thing is I have posted that worksheet that I just went over. It's on Canvas, and that way you can go over it yourself, fill it in, watch this video again, and maybe it will help you understand the process a little bit better.